Hi, I'm Matthew Henry, and I'm presenting some work I'm doing with Jeff Ballas at the University of Exeter on high CO2 climates. We have evidence from both past warm climates and projections of future climate change that the land temperature seasonality is reduced in climates with high carbon dioxide. And we wanted to explore this question in an idealized model to see if there's a robust explanation for why this reduced seasonality occurs. First, the evidence from past warm climates. This is a history of Earth's surface temperature. Note that the x-axis is broken up into different scales. Having seen this graph many times, I added these markers for reference. And one area of particular focus is the early Eocene, which was about 13 degrees warmer than today. There is also strong evidence from fossils and other proxies that temperatures were above freezing year-round at locations that reach minus 40 degrees C in winter today. And in predictions of future climates, in scenarios of high emissions, when the sea ice has melted, the land surface temperature continues to warm more in winter and less in summer than the ocean, which warms uniformly year-round. These two comprehensive models have different amounts of warming, but the seasonal pattern of warming is consistent. A few hypotheses have been put forward for this exceptionally warm Eocene Arctic continental winters, which involve different types of clouds, so convective clouds, stratospheric clouds, and near-surface clouds over land. And the seasonality of high-latitude warming under anthropogenic climate change is mainly thought to be caused by changes in sea ice. We thought we would use a very simple setup to see if there was a robust reason for the decrease in seasonality of high-latitude land in climates with high carbon dioxide. So we used the ISCA climate model, which is an offshoot of the GFDL climate model and aims to facilitate studying the climate system using a hierarchy of climate models. The particular version of ISCA we use is an atmospheric model with comprehensive radiation, a fluid dynamics scheme, a convection scheme, and a simple land surface parameterization. It does not have clouds or sea ice or ocean circulation. The continents are simply represented by having a 10 times smaller mixed layer depth, which decreases their surface heat capacity by the same amount. And we do 3 experiments which simply consist in quadrupling CO2 concentrations twice from 300 to 1200 to 4800 parts per million. Here we see the surface temperature for the 3 experiments and the surface temperature change on the right. Notice that the surface temperature change is polar amplified even in the absence of sea ice, and that even though the CO2 forcing from the second quadrupling is approximately the same as for the first, there is a much larger increase in surface temperature caused by more solar absorption in the moister atmosphere. And interestingly, the high-latitude land warms more in winter for both quadruplings of CO2. So here on the left we have the polar surface temperature for land in solid line and ocean in dashed lines for the 3 experiments, and the surface temperature change for both quadruplings on the right. Much like for comprehensive models, when the sea ice has melted, the land warms more in winter and less in summer compared to ocean, which warms uniformly year-round. So we can now use this idealized GCM to better understand why. To do that, we use the surface energy balance over land and ocean poleward of 70 degrees north. The surface temperature evolves as a function of the absorbed shortwave radiation at the surface, the downwelling long-wave radiation at the surface, the latent and sensible heat fluxes, which are imposed from GCM values, and the upwelling long-wave radiation, sigma Ts to the 4, is a function of the surface temperature. The heat capacity is 10 times smaller for continents than it is for oceans, and the surface temperature is the only remaining variable that is integrated as a function of time. When we integrate the surface temperature as a function of the GCM values for the surface energy balance model terms, we find a good match with the GCM values, which is a reassuring sanity test. We then remove the surface turbulent fluxes and the seasonality in the change in downwelling long-wave radiation, so the only difference between land and ocean is the smaller heat capacity of land. In this case, we find that there is a similar pattern to that of the GCM, i.e. a reduced seasonality over land and equal warming year-round over ocean. So you can see this in the green lines, which represent the modified surface energy balance model. This is caused by both the smaller heat capacity of land and the non-linearity of sigma T to the 4, which causes lower temperatures to warm more to emit the same amount of surface long-wave emission and balance a given forcing. We also look at the role of the increased evaporation over land in summer as a possible explanation for the seasonal pattern in warming. To do that, we remove the sensible heat flux and replace sigma T to the 4 with a linearization to remove the effect of the sigma T to the 4 non-linearity. We find that it does explain part of the seasonal pattern of warming, as can be seen in the solid green line, but it is important to note that evaporation is actually limited over land. So in the separate GCM experiment, we restrict evaporation over land and do the same analysis, and find that when evaporation is limited, the contribution of the increase in evaporation over land in summer is reduced, as can be seen in the dashed dotted line, green line. We can also look at atmospheric temperature change. At high latitudes, the atmosphere warms more near the surface in winter, as you can see on the left, and more in the upper troposphere in the summer, as you can see on the right. We relate that to the atmospheric energy budget in the control simulation. Over ocean on the right, the atmosphere is mostly in radiative advective equilibrium, whereas over land, the atmosphere is in radiative advective equilibrium in winter and radiative convective equilibrium in summer. This radiative convective equilibrium promotes upper tropospheric warming, much like in the tropics. So we can think that the land gets warm enough in summer that convection is triggered, and that then resembles the tropics more, where we see upper tropospheric warming. Whereas radiative advective equilibrium tends to promote near-surface warming. So you can see the Cronin-Janssen paper from 2016, which goes into this in detail. In summary, we have several lines of evidence that point to a reduction in seasonality over high-latitude land as CO2 is increased. We have evidence from Eocene proxies, we have evidence from comprehensive climate model simulations under high-emission scenarios, and an idealized GCM with no sea ice or clouds and a simple representation of land. Using this idealized GCM, we find that the non-linearity of sigma T to the 4 is a robust mechanism that could explain this winter amplification of high-latitude land warming. This non-linearity causes lower temperatures to warm more to emit the same amount of surface long-wave emission and balance a given forcing. When combined with the small heat capacity of land, this leads to more warming in winter than summer.